Quick! What's that behind you? Nothing? Aha! Check again. Oh, right. Also, nothing. What the What?
Let me get to spitting, cause I'll hit you with physics. Cause these equations are amazing, stay alert and look busy. You better sharpen up your shape and get ready to learn, so we can teach you all the physics from your classroom to CERN. Alright, stop.
Today, Spacetime. Spacetime is just a mathematical model which combines the three dimensions of space in which we live with time, creating this four-dimensional thing, space, which we call spacetime. If you took the universe with all of its massive things, such as stars, planets, galaxies and the looming threat of World War III, and you took all of those out, you'd be left with nothing. And that nothingness, the very fabric of the universe, the very denim upon which you sew your scout badge planets, that is spacetime. Spacetime's actually a really useful model to help us describe some of the concepts that we get in cosmology and astrophysics, such as wormholes, black holes, white holes and potholes. Maybe not that last one. Not even the county council can tell me why they're still about. So today I'm going to walk you through some of the most interesting space-time based concepts that we have in physics. There's a phrase that's something along the lines of mass influences how space-time curves, space-time influences how mass moves. But what does that actually mean? Well, in order to answer this question, I've come to one of the most high-tech scientific facilities in the UK, my bedroom. Okay, maybe I could do with tidying up a little bit. Objects that have mass cause space-time to curve, and it's this curvature that then tells other objects how to move. We can think of this fabric of the universe, space-time, as being a, well, actual piece of fabric stretched out flat. Here's one I made earlier. With no massive objects present, you can see that space-time is flat. Now if we add a massive object, in our case is an apple, you can see how the space-time around it begins to curve. In this case, the fabric begins to curve. Now if we add less massive objects, in this case Darth Vader Lego figure, you can see how the curvature of space-time due to the presence of the apple is causing Darth Vader to move. So really massive objects cause a lot of curvature in space-time, which then influences how less massive objects move. Now it's worth bearing in mind that space-time isn't a two-dimensional piece of fabric, this is just a model to represent what's going on, but it does clearly demonstrate how more massive objects cause a lot of curvature, which changes how smaller objects then move. Is this all a little too abstract? Okay, let's put it into some cosmological context. I am here, in outer space. Look, there's space-time, or at least a visual representation of it. Let's introduce something really massive. A star, like our sun. Now what happens if I place an astronaut, i.e. a smaller, less massive object, next to the star? That's right, the astronaut dies. The astronaut is going to fall into the star due to the curvature of space-time. Or, more classically, the star's gravity is going to pull the astronaut in. Space-time plays a really important role in Einstein's general theory of relativity and can help us explain why photons, particles of light, can sometimes change direction. Now you were always taught in secondary school that light can only travel in straight lines, and that is true. However, much like the spinny coin things in McDonald's, you can actually change the direction of photons using the curvature of space-time. That's what's happening when you see renders of black holes with these angelic-like halos around them. Photons emitted from behind the black hole are being bent so much by its gravity that they're reaching our eyes. So if you see these renders of black holes with this weird light halo around them, fret not, it's not the Atraxi from that one Doctor Who episode, and don't worry, Judgment Day isn't here either. Speaking of black holes, what would a black hole do to space-time? Well, we know that really massive objects curve space-time a lot, so a black hole that's really massive and really compact, it's going to curve spacetime an awful lot. So you may be thinking, if we can curve spacetime, can we curve it so much that we can connect two distant far off points? Well, in theory we can, and that, my inquisitive friend, is what a wormhole is. We haven't actually observed a wormhole yet, but we do know that in theory, on paper, they're possible. One solution of the equations of general relativity predict that, yeah, they could be possible. But that's just on paper, and just because something's on paper, it doesn't necessarily mean that it's true. Remember, space-time isn't just three-dimensional space, space-time also involves time. You could have guessed by the name. Which means that if we're connecting 2 points in space-time to make a wormhole, we're not just connecting 2 points in space, we could also be joining 2 points in time. Which means time travel. But time travel brings in a whole host of new issues again, such as timeline changes, conservation of energy violations. Besides, if someone could travel through time, who knows what they'd do? Until next time.